My name is Binod Bhattarai. I'm a graduate student at UC Merced. I'll be starting my third year this fall. So over the last few years, I've been working on dynamics of star clusters in fire simulations. And in this summer school, I got myself into a new territory. And I've been looking at resonance sweeping in bar calculus simulations, still dynamics. And I was mentored by Jason Hunt and Sarah Pearson. And I do have other collaborators that I'm going to acknowledge later on. So before I talk what resonance sweeping is and everything, so roughly half of the non-disk galaxies have a prominent rotating stellar bar at its center. So here I have an image from STSS data presented by Crook, Sander et al., where they classified observed STSS images, classified galaxies observed by STSS images based on the probability of them having a bar at its center or not. So it's interesting to look at these images and see that bars come in different shapes, sizes, orientations, and Milky Way galaxy is also a bar galaxy. So it's really interesting to look at the effect of bar in the kinematics of the disk. And that happens in a process called a resonance, which shapes the kinematics of the disk. So for resonance to occur, we need the patterns with the bar, with which the bar rotates, should be equal to certain values of the frequencies of the stars. So that happens in co-rotation resonance. That happens when the pattern speed of the bar, which is the rate of the angular rotation of the bar, gets equal to the azimuthal frequency of the star. And there's another outward bar resonance that occurs when the sum of the azimuthal frequency of the star and half of the radial frequency of the star gets equal to the pattern speed of the bar. So there are other types of resonances, but in our project, I've looked at the the effect of co-rotation resonance and outward bar resonance in the kinematics of the star. So here I have one image on the right-hand side where I got it from Denhan 2000 paper. So they show a closed orbit just inside and outside of the outward bar resonance of a rotating bar. Here the dashed circles depict the position of the inner bar resonance here at this towards the center, co-rotation resonance and outward bar resonance. And we can see that there are change of orbits orientation at the outward bar resonance, which results in crossing of closed orbits. So what I'm interested in is I'm looking at what happens when the bar slows down. And it has been shown by recently in Siva et al.'s paper that slowing bar traps stars in the disk. So as the bar slows down, the resonance sweeps across the disk and which alters the phase space of the stars outwards in the disk. And here I have a panel of plots that I extracted from Siva et al.'s paper, where they looked at different rates of the slowing of bar. So we have image on the left-hand side that shows the case for a slowing bar. So we can see that when the bar slows down, it traps stars in the V5 versus VR phase space. Whereas in the case of constant bar, we don't see that much of trapping. So we can see here the bar's pattern speed decreases from 36.8 kilometers per second per kiloparsec to 34.2 kilometers per second per kiloparsec in this case. Whereas in the constant bar case, the bar was at a constant pattern speed of these values. So we're looking at resonance sweeping in the bar galaxy using N-body simulations, as Rachel mentioned before. So these simulations are from Hunt 2021 paper, and these are based on Wildro-Dubinsky 2005 paper. I don't know the initials conditions either. And so they use test particle simulation that is without self-gravity between the particles. So what's different in our case is that we have more realistic version of the simulations. And we want to see exactly if we see the same things Siva et al. Observed in their studies. So I have two GIFs here from our simulation. The GIF on the left, I have the top-down view of the galaxy, sorry, the Asian view of the galaxy we can see prominent bar at its center, and we are looking at the disk from the bar stationary frame. And I have now selected a small portion of the galaxy so we don't know exactly, so it would be too much to say that, oh, the bar is at 25 degrees, but roughly considering that bar is at 25 degrees, so we are looking at plus minus 5 degrees in the galaxy to consider it as the region in the solar neighborhood. And I'm looking at a V5 versus R plot on the right, where we can see that as the time passes, we can see there are regions on the V5 versus R plot, which shows potential resonance regions due to different resonance conditions, or it could be due to spiral arms. So there are regions, and those regions were also were observed in Gaia DR2 data. And Michenko et al. They showed that they say in their paper that the resonance from bar and spiral arms could induce such diagonal regions. That creates such stable and unstable orbits in the phase space, and which creates these overdensities and gaps and these regions in the V5R plot. So to check for these resonance conditions, to check for all this dragging, trapping, so I first had to find the pattern speed of the bar, which is the change in bar angle over time. So to find the angle of the bar, we created a histogram of the azimuthal angle of the stars and placed them in 360 bins. So as you can see here, I have a histogram that goes from minus pi to pi, and we created, and we looked at, and we get distinct peaks here. And we calculated the bar angle by using fast Fourier transform, and it's notable that we had to select stars in a certain region as our bar sample to find the angle of the bar. So once we calculated bar angles at multiple snapshots, then I could look at the change in the angles over time, which is the pattern speed. So here I have plotted the change in bar angle with time, pattern speed over time. And we can see within the first, so we are neglecting the first 1 gigayear period, which is the burn-in period where the bar is still taking shape. So within the first 2 years, 2 gigayears, sorry, I said years, 2 gigayears, we can see that the pattern speed of the bar has a rate of change of 7.37 kilometers per second per kpc. And I'm saying this because I want to compare it with Siva et al.'s paper. And if you look at a larger range, if you look at 4 gigayear, so we got a rate of change of 5.25 kilometers per second per kpc per gigayear. So which roughly compares to Siva et al.'s slowly decelerating bar, where their rate of change in bar angle over time was roughly 3.88 kilometers per second per kpc per gigayear. But they looked at 9 gigayears time. So we have actually, while I was making this plot, our simulation ran somewhere around this point. So I have this initial preliminary data. So now, once we found the pattern speed of the bar, we need to calculate the frequencies of the simulated stars. So we tried many different methods. So one of the way I look at the frequency of the stars currently is using a gamma, which is a Python, and we have a Python module, and it was done by Vasilev et al. In 2019. So it calculates the frozen potential of the snapshot. So it calculates frequencies of that potential so that they are not totally perfect, but it's still useful to see the overall trends. So we use the frequencies omega phi, omega r, the azimuthal frequencies, and the radial frequencies to compare with the pattern speed of the bar. And again, we're doing that at an accuracy of plus minus 0.1 kilometers per second per kiloparsec. And as I mentioned previously, I'm looking at co-rotation resonance and outer limb bar resonance only in the current project. So these are the coordination resonance stars that I observed at a snapshot, which is 3.5 gigayears later in the simulation. So at that time, the bar's pattern speed was 34.2 kilometers per second per kpc. And I also identified the stars that are in outer limb bar resonance at that snapshot. And we see there are a significant number of stars that are in coordination resonance and outer limb bar resonance. And I also looked at the solar neighborhood, and there are a very few number of them in coordination resonance, roughly 346. And by solar neighborhood here, we're talking about this range in X, Y, and G axis in kiloparsecs. And also there were a little higher number of stars in outer limb bar resonance in the solar neighborhood. So one thing I noticed that if depending on how accurately we calculate the bar angle, or how accurately we calculate the frequency of the stars, and how and what closer range you want to compare those frequencies, the number of stars that are in resonance varies. So it's important to measure everything accurately. So that's something I learned. And I also looked at a V5 versus R plot. I was really curious if those results really pointed towards the resonance regions that we're expecting. And it was really interesting to see that these results are exactly at those resonance regions. For example, I want you to look at this upper panel here. We have a very prominent region towards the center. So that region corresponded to the outer limb bar resonance stars. And we have a small, less prominent region somewhere here, and that was the reason where we had coordination resonances. And I have overplotted in yellow and orange colors the coordination resonance stars in the solar neighborhood as well here. And a question may be asked, what about all these other regions? So that could be due to other resonance conditions and due to the spiral structure as well. So one of the things I was interested in is because I want to see whether or not the stars would get trapped due to the resonance as we move forward in time. So I track the stars that are trapped in coordination resonance over multiple snapshots. So I started at a snapshot 700, which is 3.5 gigayears after the simulation, and I looked at the stars that are in coordination resonance after 1.5 gigayears, which is at snapshot 1000. And I found that there was a significant number of stars that were still trapped in coordination resonance, even after 1.5 gigayears. So here in orange color, I have shown those stars that were present previously at 3.5 gigayears. And here we have these stars that are denoted by black dots. These are the same stars that are still present in coordination resonance. And they have been dragged a little bit outwards, as we can see. A significant number of them have moved outwards. So which is an evidence of resonance sweeping in case of coordination resonance. And in outer limb bar resonance as well, we saw even more clearly, and these are more distinct. There were a large number of star particles that were trapped. So in this case, the pattern speed, so in this case as well as the previous case, our pattern speed had decreased from 34.2 to 28.21. So which is, so as the pattern speed decreased, the resonance swept the stars by trapping and dragging them along. So which was really an interesting observation. So I also have been looking at other multiple snapshots, and I see that if you look at the stars that are trapped from very long back in time, those same stars slowly get drifted away. We don't see them getting trapped always. So some of them are getting not trapped and released from their orbits. And also, it was interesting to see that as we moved forward in time, the number of stars that are in coordination resonance and outer limb bar resonance is increasing. So that could be due to maybe it's carrying those trapped stars as the time passes and the bar slows down. So that's another observation. And so I've looked at a very few snapshots, and it would be too early to make any conclusion out of it. So some of the key results. from my work summer school is we calculated the pattern speed of the bar, we identified stars that are trapped by resonance with the bar, and we found significant fraction of stars remain trapped for a long time, as long as 1.5 gigayears. Now in future, we want to calculate frequencies across the whole simulations, every snapshot, and look for sweeping of stars across several snapshots and look at the kinematic imprint of the stars. We want to compare with Siva et al.'s paper and the Gaia data as well. And we want to look at the kinematics of the stars in the solar neighborhood. And also it would be cool to compare the behavior with other simulations where bar slows down at different rates. I'd like to acknowledge my mentors for their wonderful support and guidance. And I'd also like to acknowledge Rachel and Carrie developing the code that really sped up reading the files from the simulation. I'd like to acknowledge Adrian, Catherine, Martin for their valuable feedback and support, and all other mentors and students from the summer school. You guys have been great. Thank you.
Thank you so much, Binod. Elena is ready with a question. Do you know, did you estimate the fraction of stars that are trapped at co-rotation?
I have the numbers. So in snapshot 700, it was 3.5 gigayears after the simulation, a 0.14% of the stars were in rotation. And surprisingly, that percentage keeps on increasing as we move forward in time. And so whether or not this is...
I think it's consistent. So I've done similar, I mean, I haven't looked at the sweeping, but I've studied the stars that are trapped at co-rotation. Mm-hmm. That would end up to be part of the Hercules stream at the solar neighborhood. And they are around, I get the similar numbers, so between 15 and 20%. Mm-hmm. So fine, interesting. Something maybe to compare with different models, because I know that Martin has a different number, so it would be interesting to see, you know, if you have different models of galaxies, what is the fraction of trapped stars at co-rotation? Mm-hmm.
I have a question for all three of you, is how are you defining trapping? So we should start with Binod. What did you do to calculate that number?
So trapping referred to if there are certain population of stars that are still in the that are still satisfying the same resonance condition over a certain period of time, then we call it trapping.
Yeah, I guess I was meaning resonance condition. What is the resonance condition?
So that's so as the bar slows down, the pattern speed of the bar changes as well. So those stars are preferring to align themselves in such a way that they are also satisfying the resonance conditions. They're still fulfilling the resonance conditions by changing their azimuthal and radial frequencies. So I think that's the trapping.
Yeah, I guess I was meaning would it be sorry. Okay, I'll.
No, I haven't checked that. Yeah, I just identified so the way I've done is by identifying the IDs if they're still present when the same resonance occurred at certain times. So that's the way I did it so far. But yeah, that would be really a good way of confirming it even further.
No, I have a related question.
Sorry, Emily,
that wasn't a joke. Yeah. So actually, if any students have a question, we should go to you first. Okay. Well, anyway, so how can you tell if an orbit stays trapped or in resonance with the bar if you're computing the frequencies in a static model that's frozen at a snapshot that's not evolving with the evolution of the bar?
So that's a curse for us because we can't. So yeah, so as as we're working on this, so that was concerning as well. Yeah. So our frequencies are not the true frequencies that we're calculating. So yeah, I just went ahead with the analysis by estimate. So that's a rough estimate of the frequencies. So yeah, I should again stress that those are not accurate frequencies, and yeah, we are still working on improving our ways. But there are both give and takes on either methods. So if you use frozen potential, yeah, so you are only using frozen potential. That's not true. But if you use other methods like superfree, so there we have to do a trade-off of how long range in time you want to look at the frequencies. So there's always equal trade-off on any method. So we don't have, I think, a very exact proper method of finding the frequency. So that's a challenge.
I computed the orbits. So I look at, in my case, I was actually tracing back where Hercules was coming from, and I saw that they were basically, librating around the Lagrangian points, and then I looked at in the path and speed of the bar, and they had the typical, orbit of the co-rotation radii, but they were not trapped for forever. They were at a certain point they got entrapped. So, but I haven't really explored more, exactly the condition when they get entrapped, and it would be interesting. It would be interesting maybe to compare in different models as well. It would be interesting to understand a bit better this.